Okay. Hey, I do have an announcement. Quick announcement. I did post my office hours. I used the same Piazza post that Nick has. I added my uh, I added my Zoom link there. The link itself might change, so don't bookmark that link. Um, because I don't have it set up as a recurring appointment yet, so the link is going to change. So each time office hours comes, check out the new link. And I also have different links for Tuesday and Thursday. Since Tuesday, I'm sharing that link also with the 116 students. I need a separate link that's only shared with you guys for the Thursday, for all of you on the Thursday office hours. The Homework 6 due date has shifted. I haven't updated the website yet, but it'll be due next Thursday at 11:59 p.m. So almost a week extension on that. And then all other due dates are going to be the Sunday following the regular due date. So they were due on Fridays. They're all being moved back 2 days to be due that Sunday. Since and the reasoning for that is I have them due on Fridays just so the homework doesn't consume every weekend. You can get the homework. You're forced to get the homework out of the way and done with, and then you can go have Saturday and Sunday to do whatever you need to do, recharge or do other homework or whatever. That doesn't make sense. With this new configuration, all of our weekends are completely destroyed, so might as well have them do Sunday night. Homework 7 is next Sunday. Yeah, so Homework 7 would be due next Friday. It's going to be due 2 days later, that Sunday. And I'll update the website once I get a second to do that. I'm still catching up, still getting everything converted to online only. Specifically with 116, there's a lot more logistics since we have the live labs that have to be somehow simulated in this environment. It's a bit more of a pain. I almost have that. The first lab is going to be tonight, so we'll see how that's going to work out, and then I'll finally be back on track. I need to, and if anybody has feedback on the stream or any of the setup, let me know. Monday went pretty well. We have no major issues. Everything's going pretty smooth here. But if there are nitpicky issues, feel free to let me know. One thing I'm realizing, I gotta lock my chair somehow. I keep moving back and forth in my chair. So little things like that, if you notice. Anything that can improve quality of life. Reload the page so I missed part of the conversation. Yeah. Your question's right above it. So Homework 6 is due next Thursday, and Homework 7 the next Sunday. Yeah, correct. And both at 11:59 p.m. And then all the other homeworks and project deadlines. So like Project Phase 3 will be due, let's see if I can remember this, May 10th then, 2 days after the last day of class. So all those homework and project deadlines are shifted back to Sunday. Dang, you need help with Homework 6 Part 2. With that, during the Q&A after lecture, I can go over that. That is a complicated thing. I talked about it in the Q&A last time, just at a high level. I'd like to potentially give more examples. I don't know how prepared I am to give examples of that, but during the Q&A, you can watch me try to hack through it and give you more solid examples of keeping that connection open. But let's get through today's lecture. Let's talk about security, and then we can talk about that during the Q&A. We can talk about the current homework. I imagine that's what the Q&A will be used for mostly, is to talk about whatever homework is currently happening. I'd like it if we got to talk about that day's lecture content as well, but I know how reality is. You're thinking of the homework right now. You're not thinking about security. You won't think about security until we have a homework on security, unfortunately. Just like, I was talking about WebSockets, you were probably thinking about Ajax, but that's life. It's part of what I come to expect. So let's talk about this. Timothy, if you can just hang on until the Q&A, because that's going to be distracting if there's a whole conversation about something that I'm not even talking about. If we can try to limit that during these streams. So I am watching the chat. I want to know if there are questions about what I say, or if there are audio issues or anything like that. I need to be able to see that. and if there's a whole conversation about something I'm not even talking about, it's just going to be distracting. If you do want to have a conversation about that, we always have Piazza. You can go there and have a conversation about that. Of course, you probably get better response here. I assume that's what you're doing. Anyway, let's do some lecture, and then I can join that conversation. So we have this big problem. Is this the slide I want to be in? Yeah. I got a few slides ahead. Okay. Stream is good. Good. Nice to hear. Yeah, like I said, any nitpicky things, we can start improving quality of life at this point. I think we're pretty well up and running. No major issues, at least so far. But any quality of life improvements, audio level adjustments, and things like that, just let me know. So HTTPS, this is what we're eventually talking about. We have this public-private key encryption that we talked about last time. This RSA is one example of public key encryption, a public key crypto system, where the server is going to generate a public and private key pair, share their public key with the world, and keep their private key private. And now whenever somebody wants to send a message to that server, they could encrypt with the public key and send that message to the server, and the server can sign messages with their private key and say, this is actually me, I did send this message, and that can be verified with that public key. There's one big problem with this that needs to be addressed, which is addressed, which we'll talk about, is this man-in-the-middle attack during the request for the cert. So the first thing that has to happen with HTTPS, if we want to encrypt traffic online, is the client's going to say, hey, I'm here, I want to talk to you, I want to talk to this server, send me your public key. Well, what if somebody intercepts that message, and instead of sending that message to the server and getting the server's public key, the attacker replaces that, captures that traffic, and then responds with their public key. You have a public key, it looks like it came from the server, you're going to encrypt with that public key, but the only people who can read those messages is this attacker, this person who intercepted that message. So we need some way to verify that the public key we get is actually the public key of that server. And this is where certificate authorities come in. This is where certificates, which you've probably heard of, certificates come into play. So we don't just want the public key. We want somebody to verify that that public key is actually the public key of the server. And that's what a certificate authority is going to do. So a certificate authority is an entity with a known public key. We know that we have the actual public key of the certificate authority. This is an assumption. Depending on your outlook, it's a fairly strong assumption. But we gain this assumption by pre-installing them with our browsers and with our operating systems. So our machines, when we download the software and install the software, it comes with these, what we call root certificates, which are the public keys, contain the public keys of these certificate authorities, these root certificate authorities, as we'll see in a minute. So we have those installed, and we assume that the installation process went well. If you were really paranoid about this, or really want to make sure that you have all of the proper certificate authority keys, then you could download the executable, whatever you're installing, whatever browser you're installing, and then verify the hash. The hashes of the files that you download are typically provided around somewhere near the download link. You can download the file, hash that file, and then make sure the hash matches the one that you expect to verify that what you downloaded is in fact the executable or the installation, whatever it is, for the browser that you're expecting. So there are ways that you can go that next level of security. For most of us, we just assume that we download that browser, we install that browser, and that those certificates are valid. If we download our OS, or our machine comes shipped with an OS, any certificates pre-installed in that process, we're going to assume those are valid. So we assume no man-in-the-middle attack right there. And by the way, security, no matter how advanced the crypto system, no matter how advanced the technology, the algorithms and everything, there's always a root assumption with all security. Something has to be assumed to be secure, and then that's where all of our security comes from. For us, for the internet, it's assuming that we have the proper certificate of root CA certificates and that there was no man-in-the-middle attack during that installation process. That's where all of our security is based on for the internet, is that these root CAs are valid. Sometimes they are invalid. There have been notable attacks in the past where a root CA was not valid, that somebody was able to get an attack certificate installed in a lot of machines, and that can do a lot of damage because that's what all of our security is based on. Anybody using that root CA is now compromised in that case. So bad stuff can happen, but we're going to assume that these root CAs are valid. So the root CA, they take so you have their public key for the certificate authority. Then the certificate authority, whenever a new domain is up and online, they're going to either generate their, actually I don't think they generate their own these days. They're going to go to the CA and say, hey, can I have a cert for my domain? The certificate authority is going to generate the server. The logistics are important, but anyway, the certificate authority is going to sign the public key for that domain, and then also give some details about who the certificate authority is, who the domain is for this public key, and have that as a certificate. The certificate authority has the certificate, most importantly has the public key, but is signed by the certificate authority. We have the certificate authority's public key. They sign that with their private key, and now we can verify that the certificate authority did verify that this is the public key for that server. So then when we go to a new website, we're going to get their certificate. We're going to verify that certificate with the CA's public key to make sure that the CA did sign this certificate, that there was no man-in-the-middle attack, who the man-in-the-middle would not have the CA's private key, so they wouldn't be able to sign this. We know there's no man-in-the-middle, and we know that we are actually talking to the server that we expect to be talking to. So we verify with that CA's public key, and now we know that we have the actual public key of the server that we're expecting to talk to. So that's how we're able to verify that. Verify that we do have the correct public key. Without these certificate authorities, we really wouldn't have much. We'd be completely vulnerable to the man-in-the-middle attacks, and we wouldn't have too much security. So an attacker like the government NSA could replace the public key with a different one. The government and NSA actually don't play a role in this. They're just as in the dark as anyone else. That's one of the big features of the internet and this security. Government and NSA, there's no oversight organization like that, so they can't get in our business. This is why the government and NSA, they kind of don't like all this encryption that we're doing. And there's current news out there. The Senate's trying to pass a bill that's going to hurt internet security. The government doesn't really like all this stuff. They'd rather be... I shouldn't talk so generally, but there are people in government who would rather be spying on us. Spying's maybe a little strong word, but they'd rather not us do things that they don't know about. The certificate authorities are separate organizations, separate from the government. They're in the private sector. And they've just established enough trust that we end up trusting them. But there are a lot of certificate authorities. If one of them does something that diminishes our trust in them, our collective trust, sites just aren't going to use that certificate authority anymore. They'll fall out of favor real quick. How do we trust a CA not to be another man in the middle? Yeah, exactly. We just have to trust them. That if a CA themselves act in bad faith, we're screwed. So we have to trust these certificate authorities. So that Snowed movie was whack. I haven't seen it, to be honest. But, I mean, there is a lot of... I'm talking in the context of certificate authorities. The government and NSA don't control certificate authorities, at least not to my knowledge. I mean, that doesn't mean they don't have other things that they do. They have other means to do some things we might not want them to be doing, or might want them to be doing. Depends on your outlook. I am not taking a stance on that one. So So we have these, what we call root CAs, installed on our machine. But when we get a certificate for a website, it's not always signed by a root CA. In fact, it's often not. I haven't found any. I haven't visited any websites where I checked the cert and had it actually signed by a root CA. But what does happen is the root CA is going to sign the certificate of a different certificate authority, another CA. So we have these CAs that have their certs signed by a root CA, which creates somewhat of a keychain, which can be, as long as it needs to be, as long as the root of that keychain is a root CA. So if the root CA signs a CA cert that signs another CA cert that signs another CA cert that signs the domain cert that you're visiting, as long as that chain leads to a root CA, we're going to trust that these are the actual people involved. These are all the correct authorities. These are this is actually that domain's public key. The root CAs really aren't out there signing domain names, but they are signing CA certs, and then the CAs sign the domain certs. So if we have some cert, Let's Encrypt, we'll see an example of this on Friday. A Let's Encrypt certificate, which is a free certificate authority out there with automated tools that lets us sign certs real easy. CC312.com, that's signed by a Let's Encrypt certificate. So Let's Encrypt is signed by some root CA, and then Let's Encrypt signs the cert for our domain. Let's Encrypt signed CC312.com, that cert, and Let's Encrypt was signed by some root CA. And I'll actually show that in the browser in a second. So there's some keychain that eventually leads to a root CA that's pre-installed on your machine, but there might be an intermediate CA that's not pre-installed that's verified through that root CA. So we get this keychain. As long as the keychain leads to a root CA, we're good. If the keychain does not lead to a root CA, which is going to be the case in our homework in homework 7, this is what we call a self-signed certificate, and you should not trust these. There's no guarantee that you did not have a man-in-the-middle attack. There's no guarantee that you actually have the proper public key for that server. For the homework, we'll use self-signed. Just for the example, you can presumably trust your own self-signed cert, especially for development on localhost. But if you're out there on the internet and you get a self-signed certificate, you're going to get all the warnings, and this certificate is invalid and everything. Your browser is going to let you know, under no uncertain terms, that site has a self-signed cert. This will happen with your homework too. Your browser is going to have all kinds of flashing bells, whistles, and everything. It's going to say, you really shouldn't be here. This is a self-signed cert. You cannot trust this site. And then you have to override those settings to actually go to your site and test out your HTTPS for the assignment. But you will have a self-signed cert. The CA, like Let's Encrypt, they're going to need a domain name. So we could have the homework set up to use Let's Encrypt, for example, but they're going to need a domain name, and I'm not going to require everybody to purchase a domain name just to get rid of the warnings on the assignment. But on Friday, I'll show an example of having a domain name and getting a valid cert that's signed by a root CA. You quickly explain again what the signing does. I'm actually going to go to an example, so through that example, I can talk about that. So let's go to CC312.com, and we get this lock in the browser. You've probably seen these before. You probably know what this is about, at least at some level. This lock means your traffic is encrypted. Specifically, this means we're using HTTPS. If we click on this lock, we can check out the certificate and see some information about this certificate that we have. So we can see Let's Encrypt, authority X3. They have different authorities. There's different Let's Encrypt authorities. They signed this cert, and it was issued to this domain name. This cert is for cc312.com and no other server. That's what this cert is verifying. We can get a lot of the information, including the public key. The most important piece of information that we need, the whole reason the cert exists, is for this public key. We have a public key and a variety of other information for us to for us to consume, for our browsers to consume, that that guarantees this is what it's supposed to be, including a few algorithms. The algorithm that's used for encryption, this is a 2K bit RSA scheme, 2-bit key size, 2K bit key size. So when we're talking about the size of P and Q, the size of P and Q is in order of 2,000 bits in this for this public key. And hashing algorithms, we're using SHA-256. This is to sign the hash. So getting back to your question, what does the signing do? The certificate authority is going to sign a hash of this certificate. So this certificate, and is it that looks like it actually, thumbprint or the signature? No, it's one of those things. So one of these is the actual signature of the CA, which takes the bytes of this certificate, hashes them using SHA-256, hashes the certificate, and then signs that hash with their private key. So what our browser is going to do is it's going to get this cert, hash it using SHA-256 to get that hash of the certificate, and then verify that hash, the signature of the certificate, with that hash. So they're going to take this signature from the root CA, not decrypt, but verify the signature using that CA's public key. And if that signature verifies to exactly that SHA-256 hash of the certificate, then we know that the CA did verify this certificate with their private key. So we check that. I'm going to assume that's what the thumbprint is the signature of the hash. And then the no. I lost that other one. I'm going to assume this is the signature of the hash. But but they're going to sign that hash, and that's going to verify that the bytes that I'm looking at for the certificate are the exact same bytes that the CA was looking at when they verified this certificate. So then I know that the CA did verify that this certificate is legit, and then I can start trusting the certificate. And if we look at this last tab, the certificate path, if I have the cert for CC312 that I'm looking at, this was signed by Let's Encrypt Authority X3. And I can look at their cert. I can see all the details for this, what algorithms they use. They also use 2K RSA. They also use SHA-256, etc. But if I go to... Oh, I had this set up. I was supposed to get this far in Monday's lecture. Now I realize that was way off. But, so I got to open it up again. I'm halfway through this lecture, still haven't gotten there. So I can look at the certs that I have installed on my browser. If I go to Trusted Root Certificates, I can see a list of every certificate that this machine in this browser trusts. And if I look in here, if I go to the L's, I don't even think there are any L's. I'm not going to see Let's Encrypt anywhere in here. But if I can remember... There it is. But DST root CA X3, this is pre-installed on my machine. I can take a look at the cert. They're going to use... Damn it, cert, don't make a fool of me. I was going to say they use stronger encryption. The root CAs, I thought, were usually 4K key sizes. But anyway, SHA-1 is the signature algorithm, so different but same effect. But I can see their public key. So this public key is used to verify Let's Encrypt cert, and then Let's Encrypt's public key is used to verify the CC312 cert. Yeah, another 2K. I thought they were 4K. So I do trust DTS root CAX3. If we go back to the cert chain, that is the root CA that signed this cert. So CC312, through its keychain was signed by this root DST root CAX3. If you go into your search settings, you're going to see this DST root CAX3 also in your root CA certificates. You have that pre-installed in your machine. We have the same exact public key, the same exact cert for that root CA from DST. If you didn't, I mean, I guess it's possible you don't. I would highly doubt that. But if you didn't, when you go to CSE312.com, you would see all kinds of errors. It would say, you should get the hell out of here because this is not a trusted connection. If you haven't seen all those warnings and errors and you get this green lock, that means you have DST root CAX3 installed on your machine. You have that root CA and your browser was able to verify CSE312's certificate based on that. I DuckDuckGo Google. How weird. And we can look at other certs. I want to get on to the rest of the stuff. But like for example, Google. People tend to trust Google. Google actually has its own certificate authorities. It issued I guess Global Sign. I guess they use Global Sign, but then have their own root CA. Anyway, Google does a whole bunch of advanced stuff on the internet. Anyway, you can look at any cert chain, but Google's certificate isn't even signed by root CA. They even have an intermediate, for what it's worth. I thought that was going to be more interesting. I kind of regret pulling up the Google thing now. Anyway, let's get on with this. We got this. All right. Let's talk about HTTP over SSL / TLS in 20 minutes. I'll try to go fairly quick through this. There's not too many slides, but some of these slides are pretty dense. So I'll probably end up finishing this up on Friday as well. It seems to be a theme. I'm still getting the feel for how long these lectures take in 312. But also I tend to get sidetracked and give way more detail than is on the slide. And that keeps hanging me up. But anyway, HTTPS. Commonly called HTTP secure, technically HTTP secure, just the order of the letters, or secure HTTP just kind of flows off the tongue better, I think. But what this actually is HTTP over TLS or SSL. I'll talk about that in a second. But this is the same from our perspective, from web app development, from the web app developer perspective, in a web developer frame of mind. HTTPS is the exact same protocol as HTTP, and all of the code that we write for using HTTP, we're going to reuse every single character of that code when we use HTTPS. HTTPS is a layer that we're adding on top of HTTP, and it does not affect our HTTP code at all. So everything you wrote in every homework, we can add that little S to the end of HTTP and have all of that be secure. And today we want to talk about how that works and what that means. So there's no huge refactor in our HTTP code to add security. There's only a refactor in between HTTP and TCP, as we'll see in a second. But first, SSL and TLS, these are used somewhat synonymously. We touched on this on Monday, but I just want to make sure this is clear. If you see SSL or TLS, those are referring to effectively, somewhat the same thing. So secure socket layer was the protocol that did all this. We had HTTP over SSL, secure socket layer, and SSL had 3 versions, 1.0, 2.0, 3.0. And when they got to 4.0, instead of calling it SSL 4.0, they called it TLS 1.0. They just changed the name. It's the same solution to the same problem. It's the next step of the next evolution of this protocol. They just renamed it to transport layer security instead of secure socket layer. I don't know why. I'm sure there's some interesting story out there. I don't know it. But if you see SSL or TLS, they're used pretty interchangeably. TLS is just the new name for this protocol, and I'll refer to it as TLS moving forward. But if you see SSL, and you will see SSL, a lot of the libraries that you pull in, it's quite likely that the library you end up using for homework 7 is going to be called SSL. It'll have SSL somewhere in its name because they didn't change all the library names to reflect the change to TLS. They're not going to change all of this. I don't even know why they changed the name of the protocol, but I'm sure there's a good reason. I just don't know it. So you'll probably pull in an SSL library, but that library is going to do TLS these days because the libraries just didn't change their names. So if you're importing SSL these days, you're probably actually importing a TLS library. So I'll just use TLS from now on. Like a library we'll talk about on Friday is called OpenSSL, and it's pretty much the primary library that's used to actually implement TLS these days. It's OpenSSL. But they still call it OpenSSL and not OpenTLS. So anyway, let's get on with it. So TLS is going to be added to our network stack, or our protocol stack, which used to be this. We have the internet protocol, which is handling how our packets are routed through the internet. We have TCP, which is ensuring reliability, making sure that we do get the messages that we're sending back and forth. TCP breaks a message that we want to send into individual IP packets. And then if a packet isn't arrived, it has the resend requests and everything to make sure that we actually get the full message, to make IP reliable, to make sure that we're getting all the information that we send. And then we added HTTP on top of that. We write our HTTP request parsing code and write our responses, and then we send that over the TCP socket. So this is the network stack that we've been using so far. We haven't been concerned about IP at all. We write our HTTP server, and then that server communicates via a TCP socket. And right after we say TCP, here's my bytes, go send this to the client. We don't think about it after that. The libraries take care of it after that. Now what we want to add for homework 7 is this TLS layer, which fits right in between HTTP and TCP. So now instead of writing our HTTP responses and getting our requests and using the TCP socket directly, we're going to add this TLS layer, which is going to add the encryption to our TCP communication. So any request we receive over the TCP socket is going to be encrypted. We're going to put that through our TLS library. TLS is going to decrypt it, and then we're going to send that to our HTTP server just as we did before. It's going to be an unencrypted HTTP message with headers and content length and a body and all that good stuff, if it's a post, I guess. It's going to have all that good stuff that we've been working with all semester. So by the time our HTTP server sees it, it's going to be unencrypted. It's going to look just like an HTTP request. Our HTTP code will not know and will not care that this request was encrypted at some point. Same thing in the other direction. Our HTTP server is going to write that response. It's going to give those bytes to the TLS library. It's going to give it to TLS. TLS is going to encrypt it and then give it to TCP and send the encrypted bytes over TCP. So neither TCP nor HTTP really care that encryption is even happening. These protocols work completely independent of each other, but we're adding this layer. Instead of HTTP talking to the TCP socket directly, we're going to add this layer of TLS right in between them and have TLS worry about all of the encryption in both directions, receiving and sending messages over the TCP socket. So we don't have to change any code here. We might have to change some code here just depending on the libraries that you're using. But we don't really have to change anything with the way TCP works. We just have to get this extra layer right in the middle of HTTP and TCP. Which for the homework may, depending on your setup, your architecture, and your ability to read technical documentation and get the job done, might be really easy or might be a big headache. It just depends on how easy it is to get this layer. Pull in a library and get this layer in here. And we'll dive into some code on Friday and see how that what that might look like. So all of our code is the same. We're just slipping this extra layer, this extra protocol into our stack. All right. So TLS, what is this? We're just adding this protocol to our stack, but what is this protocol? So what we want here is two-way encrypted traffic. And what we have is a server with a public-private key, and the public key is verified by a CA. So we know we have a server with a known public key that's verified. They have a private key, and we want to use that to get to two-way encrypted traffic. There's a few problems with this, not the least of which is the server can't encrypt messages to send to the client. They would need a public key of the client, and then the client would have to get that public key verified. There'd have to be a process to be able to make sure that they have the proper public key, which, there are different solutions to this that we could have. You could have the client... no, that doesn't really work. I'm not going to try to spitball that. You could have the client encrypt their public key with the server's public key and then send that. But everybody has that public key. There's no guarantee that came from the client. So we have some issues that have to be resolved. We have to have some way of the server encrypting messages to the client. Is one of probably the most glaring issue that we have with this. Client sending messages to the server, no problem. Just use their public key, send it over, done. There is one other problem with that, is that I don't have on a slide. I'll mention it here. Public key encryption is actually really slow. It's not too bad, but if it's slow enough that it's going to add a little bit more delay on every page load and everything that happens on the internet. We don't really want that. We want speed. We want efficiency. So we want a faster encryption algorithm, and an encryption algorithm that's going to work in both directions. So with TLS, we're going to have another handshake. A lot of handshakes and protocols. The client and server are going to negotiate how they're going to use TLS. They're going to agree on what's called a symmetric encryption key using a different encryption algorithm. AES in the example we'll see. I won't go into the details of AES, but suffice to say, a symmetric encryption key means that the same key is going to encrypt and decrypt, and both client and server are going to have that key. They're going to have a shared symmetric encryption key, and symmetric encryption is a lot faster than public key encryption. And now they're going to use this shared symmetric encryption key in all of their communication, to encrypt all their communication in both directions. So the objective, the new updated objective, is using only the server's public and private key that's verified. That's the only thing we have to work with here. Using only that, how do we negotiate this symmetric encryption key without any eavesdroppers being able to know what the key is? So if somebody's listening in on all of our communication, which we should always assume somebody's doing, even if they're not, it's always possible. Somebody can be, all they have to do is be in Wi-Fi range to see all of this communication. So how do we negotiate this symmetric key encryption? And the whole point of this is to get encryption up and running. So the answer of, well, let's just encrypt all this traffic is not a valid answer. We're trying to get to the point where we can encrypt something. Right now, the only thing we can encrypt is messages from the client to the server. So just encrypt everything isn't a valid answer because we don't have encryption set up yet. So how do we do this in a secure way? So one way to do this, and I'll mention here, there are lots of different algorithms out there in practice. There are tons of different algorithms that are used. I'm going over RSA and Diffie-Hellman are the two examples I'll go into and actually show the math on, partly because they're pretty straightforward. It's an example that we can all wrap our heads around and see at least one solution of how this could be solved without diving into the whole world of cryptography and checking out all the latest fancy algorithms and elliptical curves and all that cool stuff. I don't even have enough time to go through this stuff, so I can't go through all that. But Plus, I'm not prepared for that. I'd have to study it up again. Anyway, the client and server. Let's talk about the Diffie-Hellman key exchange. This is one way that they can agree on a shared symmetric key and have that private to any eavesdroppers. Client and server, the first step, are going to agree on some prime number G and a group generator for P called G. A generator, this is all advanced algebra techniques. If you're interested in algebra, if you're interested in cryptography, you should take advanced algebra classes. But the really short explanation, a group is going to be the numbers from 1 to p minus 1. That's a group of numbers. And a generator G is a value in that group such that each value from I to p minus 1, or from 1 to p minus 1, G to the I is going to be a unique value. So this G generates the whole group, meaning if we keep multiplying G by itself, we're going to get every single value from 1 to p minus 1. So if we keep modulo p. So if we keep multiplying G by itself, or G to any exponent, we're going to get the full effect of the whole group. We're not wasting any numbers from 1 to p minus 1. Well, we're getting every single value out of this generator. So if we take G to any value I, it has effectively the equal probability to hit any number 1 to p minus 1. This isn't true for all values in a group. There are values in a group that might not hit every value. If it hits every other value, for example, you effectively have your group size halved, and based on wanting to have large p and large values that are hard to break, cutting our group size down is bad. But let's not go down abstract algebra too far. So both P and G are public. Everybody gets to know these values. The client and server, each independently, are going to generate a random number. We're going to call the client's number A and the server's number B, just because this is the values that Wikipedia uses. Is that horrible to say that? But these are the values that the Diffie-Hellman key exchange, if you look up other information about it, those are the values they're going to use. So that's what I'll call them too, just for consistency. I linked to the Wikipedia page. I better use the same variables. Anyway, client and server, they're going to generate their random numbers. These are both private numbers. Nobody gets to know these, not even the client and server, the other side of the communication. The server cannot know A, the client cannot know B. That's part of this algorithm, is that these are completely private to each other. They're similar to private keys, but not quite the same. That we'll see in a second. Client's going to compute G to the A mod P. Server's going to compute G to the B mod P, and they're going to trade these values. So the server is going to receive G to the A mod P. The client's going to receive G to the B mod P. Each side, client and server, will take that value they receive and raise it to their value, their hidden value, mod P. And now both sides have G to the AB mod P. Since this multiplication is commutative, these are going to be the same values, whether it was G to the A to the B or G to the B to the A mod P, we're going to have the same values. So client and server now have the same value. It's a shared value based on numbers A and B that nobody else knows. So the client doesn't know B, the server doesn't know A, but they still have a shared value that's both based on both A and B. Oh, yeah, right here. I just want to make sure I said this at the right part. So they have this shared secret, and this can be used either as a symmetric encryption key or more usually used to generate a symmetric encryption key. So client and server both have a shared random number. They could use that to seed some RNG to generate random numbers, whatever they need to do, whatever specific algorithms they're using for this encryption. they can use this shared secret to be able to generate the encryption key or keys that they need. Now, there's one big problem, but what seems to be a problem here is G to the A mod P and G to the B mod P are both sent in the clear. These can't really be encrypted. I mean, technically the client can encrypt sending to the server, but the other direction can't be encrypted. We have no way of doing that. No way set up. So these are out in the clear. But luckily, what we talked about with RSA last time, to be able to take this value, for example, and compute A is exactly solving the discrete logarithm problem, which is one of our cryptographic primitives. We assume that's hard, and as long as our crypto system reduces to solving discrete log with a large prime and a generator, that is, we consider that to be secure. We just believe that that's a very difficult problem to solve. So sending these in the clear is fine. Anybody can read these values, but they can't find A, they can't find B. So for example, if you could take this and find A, and you intercept G to the B mod P as well, you take this, raise it to the A, you have the secret, everything's broken. So nobody should be able to take this and compute A or B. And since it's exactly the discrete log problem, we're comfortable with those being out in the clear. Once we have that key, once we have that secret, we're going to use that to generate the symmetric encryption keys. One common way to do this these days is AES. This is, I believe, pretty much the standard. Once you have all the key exchange and everything happens between that TLS handshake, I believe it's pretty much always AES that's being used in the end. I'm not going to go over the details of AES, partly because I find it a little boring, but I'll give a very brief overview of it. It's if you created your own cryptographic cipher, AES is kind of what that would naturally evolve into, at least in my opinion. So if you're creating your own cipher, you want to hide some text, you would start with all the bytes of your message and then just mix them up in different ways, and then send that scrambled message to to whoever you want to communicate with, but also agree on a way for them to descramble. So like the simplest one would be like a substitution cipher, where you take the letters A to Z and map each one of those to a random letter, and then send that your message with all the letters replaced to the other side, and then also agree on what that mapping is, so they can demap it. AES is taking those ideas and just running with them for an extended period of time, for decades. Researchers doing this for decades. It involves a lot of scrambling the bytes, putting the bytes in a big matrix, scrambling the rows, scrambling the columns of that, XORing them with values generated from the encryption key, using the encryption key to seed some RNG, using key expansion algorithms, they call them, and then keep repeating that process over and over and over, doing multiple rounds of scrambling up the bytes, XORing them with a bunch of values generated by the key, scrambling the bytes again, XORing them with a bunch of values generated by the key, and the scrambling itself is generated based on the key as well. It's a very convoluted algorithm, but it's convoluted in a predictable way if you have the key. If you don't have the key, there's no known practical way to descramble everything and de-XOR everything to get back to the original message. But if you have the key, you go through and effectively undo all of the scrambling and all the XORing and be able to get back to the original message. AES notably does not reduce to a cryptographic primitive. It's just based on scrambling the crap out of these bytes in a deterministic way, so it can be descrambled with the same key. There are theoretical attacks on this. Since there is no cryptographic primitive, there can be successful attacks, but so far there's no known practical attack to be able to quickly descramble these without the key, or to be able to generate the key based on the messages that you have. So as long as we have that secret key and we use AES, we're pretty confident that encryption is going to work. There have been attacks. There used to be DES before AES, and there were practical attacks made for that. So the crypto community came up with the next standard, and this is I believe this one was led by the NSA, or it was a government organization that led the charge for this standard. They put out a call for proposals. A lot of research teams submitted their proposal, and the best one was chosen. So this had some government involvement to be able to agree on this standard, for what it's worth. So for TLS, how does all this fit into TLS? It's 10:51. I do have a few. Do I want to revisit this next time though? Yeah, let's quickly talk about this. With TLS, at least 1.2, they changed the handshake in 1.3 to be to have less back and forth. But the client is going to say, here's all the algorithms I support. Server is going to respond with the algorithms that we're going to use for this connection and their certificate. Client and server, both now that they both know what algorithms we're using, are going to generate whatever they can for the symmetric key, their parts of it. In the protocol, it's typically led by the client. The client computes their part of the symmetric key and then sends that part over to the server, and then the server finishes up their part. So if they're depending on what algorithms they're using, whatever they end up using, they compute their parts, send their parts over, and then compute the rest. Once they receive the part from the other side, they'll compute the rest of the symmetric key. Now they both have the symmetric key, and they can encrypt all their traffic back and forth. The algorithms themselves are not. There's no, like, if you're using TLS 1.2, you use RSA, you use Diffie-Hellman key exchange. The algorithms are not specified. That's not the case. The algorithms can change over time. They can evolve. They can be replaced. And that negotiation happens on a per connection basis. So if a new algorithm is out there, the browsers will start supporting it, servers will start supporting it, and then in those hello messages, they can start agreeing to use that new algorithm that came out. But there need to be algorithms for the key exchange, algorithms for the symmetric key encryption, and any other algorithms that need to be added. How are we going to pad our RSA hashing, if that's something that needs to be done? All of those algorithms are going to be decided during this handshake. Now, notably, I haven't mentioned, this is the last thing I'll say, and then I'll move to the Q&A. Throughout everything I just said about TLS, I have not mentioned the certificate yet. I haven't mentioned that. The certificate that's signed by the CA, we went through all that work to get this signed public key, but I haven't even mentioned it until this part. When the server sends their part of the symmetric key, so that would be whenever the server is sending, if we were using the Diffie-Hellman key exchange, whenever they're sending G to the B, I think A was the client's one, when they're sending G to the B mod P, they would sign that with their private key from the cert, and then the client has a guarantee that that part of the symmetric key did in fact come from the server. And that's it. That's all we're using the cert for. We're not even using that cert for encryption in any of this handshake. We're only using that for the server to verify that their part of the symmetric key was actually generated by them. So we know that that half of the symmetric key came from the server. So if we build the rest of the symmetric key based on that assumption that other half of the symmetric key came from the server, even if all of the rest of the traffic is compromised, we know that we have a key that could have only been generated by the server, so only the server can read those messages. So if the server signs their part of the shared symmetric key, sends that, and then the server is completely taken over. Well, that's a bad example because they'll just have all the private keys. But if the server goes offline and from then on you're just communicating with an attacker, that attacker can't read any of those messages because they don't have that value B. They don't have the symmetric key. So we do get the verification just by the server signing that one part of this handshake. We get the the confidence that we need. But that key in the cert actually isn't used for any of the encryption that we any of the traffic that we actually send over the internet.